IVPs, initial value problems, because we'd like to. Initial value problems will always be with us, okay, from here on out. It's just the differential equations might get a little trickier. Right now, the only kind of differential equation you've seen is one of the form dy dx equals some function of x. Or possibly, ooh, tricky, like d squared y over dx squared equals some function of x, right? But today we want to look at differential equations that are slightly more complicated. They're called separable differential equations, but it's not too terrible to recognize these. I do want you to start appreciating, I guess before we even say too much into this lecture, I do want you to start appreciating the fact that most differential equations that you might write down are actually ones that you can't solve very easily, and maybe nobody can, right? So for example, here's a differential equation of a type that you don't know how to solve yet, right? It sounds really simple, but we're looking, just to say it in words, we're looking for a function that has for its derivative the function itself minus x, the variable x, right? So you can think, you could like try some functions on for size, you know, but it would be hard to think of a function that has as its derivative itself minus x. Does that make sense what the requirement would be? If someone, again, it would be very easy to check someone's solution if they came to you. If I said, okay, I have a function I think that works, you would be like, okay, well let's see. Take the derivative. Is the derivative equal to your function that you said, minus x? It would be easy to check, but it's very hard to produce such a solution, even though it is possible. So I just thought I'd say that it is easy to see such equations. So here's a differential equation, for example. The first kind I just showed you a second ago is not one that we'll ever cover how to solve in this class. Super, like I said, super easy to write down differential equations that you can't solve symbolically. So here's the first one we'll encounter today, and this one, even though this one might look hard compared to the one I just gave you a second ago, which I told you was one you couldn't do. This one we actually can do using this technique called separation of variables. So separable differential equations. The first thing to do would be to recognize that this is separable, but I don't know that you'll recognize that yet. So we'll show you how to do this, and then you'll be like, I think you'll start to see why and when this is appropriate. So the thing I'm going to do first is I'm going to move everything that has a y in it over to the left side, everything that has an x in it over the other to the right side, and then first of all do agree my algebra works. And then integrate with respect to x is what I'm choosing to integrate with respect to. Yeah. So integrating with respect to x, I'm just slapping an integral and a dx on both sides. And again, I think it makes sense that we can do this because integration is just the process of like adding up stuff. That's all it is. And so if we have two things that are equal, is it okay to like integrate both sides? And I think that will make sense for us and add them all up. So hopefully you see what I did in the next line. It's like a thing I guess we're allowed to do on both sides, integrate both sides. Notice here that if you trust this kind of, we're playing fast and loose a little bit here, but we now have this integral if we are allowed to do this kind of algebra with the differential. So on the right side, you have an integral of a form that you kind of recognize. It's got an x, a function of x, and a dx. Yay! And on the left, though, you also have an equally nice integral. It's a function of y and a dy. So I think we're like set because both of those integrals are ones you know, aren't they? In this first example, even though it looked complicated, we actually only need the power rule in our lives, don't we? So what's the antiderivative of y to the negative 1/2? I don't know. I have to think about it too. It's y to the 1/2 times something maybe times 2. Is that right? And on the right, we need a 1/3 x cubed or something. Plus c. Now, I've only added one c here. Why is that needed? Why is only one c needed here? Explain. It seems like you might need like a c1 on the left and a c2 on the right or something. Yeah. Do you need her to say that again? No? Okay. Yeah, what she said. Right. All right, and then applying the very simple initial conditions here. If you plug 0 in here and here, it should be clear that C needs to, in this case, just be 0. I didn't want that to be the focus of this first example, so that's not a stumbling block. So I think what we have here, if you look at this last equation, is simply that C is 0, so we have this relationship. Yay. And that's actually not a bad way to write the answer. I mean, it's okay to write your answer as an implicit solution, right? Like that's maybe an okay way to do this. This gives a curve in the plane. This gives a solution curve somehow in the plane. It would be okay to say this, though. You could solve it. And there might be some other nuance there, but we'll save that for the next one. We're going to come back to that. That's a good first discussion of how to solve a separable differential equation. I hope you see that the one I gave you earlier on the first slide, what was it? I just made it up off the top of my head, but I think I said, what was it, y minus x or something? dy dx equals. I hope you see why that is in fact not separable, right? Because if you try to do what we've just talked about here, you might be thinking like, well, I could like do this, right? I can move the y's over to one side and the x's over the other. But then when you multiply through by dx here, you're still gonna have, like, you're gonna have another dx here then, aren't you? Like on the y. If we try to actually integrate this, we'll get like y dx. I'm just multiplying through by dx here. Everything multiplied by dx. So then when we go to like actually try to add these up, like this is weird. You know? So even though it's as simple as that looks, that isn't separable, and it's not one that we're even going to talk about in this class, as simple as it might look. So separable, we want maybe something like this, right? The one we're working on here. Or how about this, which maybe doesn't appear separable at first, but it is. So give it a try here. At least get the first step down on paper. Yeah, I mean, they're essentially the same thing. Yeah. Algebraically, to like justify one, you could just put an integral sign there, right? Technically, you should be able to integrate with respect to the same thing on both sides. So that's why I kind of have to get into what I do. But in practice, I don't usually write it that way. I do it the way you do. Yeah, almost. The fact that I have a y prime there actually like kind of almost bothers you. Most at this point in this process, you almost prefer Leibniz notation, don't you? By the way, I guess I'll show you the curve afterward here. So let's actually work the problem here. How are we doing on it here? So we have I guess maybe we can just write it down in one fell swoop here. 3 minus y squared dy equals integral 2x plus 1 dx. So there's the separation and two integrals we know how to do. So we'll go ahead and do those. What do we get? 3y minus 1/3 y cubed plus c. Okay, but then also 1, 0. X equals 1, y equals 0 is in the curve. So what do we get? If we apply the initial conditions, what do we get? 0 on the right, and 2 plus c on the 0 on the left, and 2 plus c on the right. So I think I see that c is negative 2. So now, interestingly, like I commented briefly on this on the previous slide, but I think we would see here that it's not easy, perhaps it's not possible to even solve for y here, right? And is that okay? Sure. Not a problem. Sometimes you're going to get an implicit solution. In fact, this should feel, doesn't it feel a little bit like the reverse of a process we did earlier this year, doesn't it? Like I gave you this and I said find the derivative, and you used implicit differentiation, and the answer you got was, oh, I don't know, something like this, right? So this does feel a little familiar in that sense. So. And then I do have the picture of this curve right here. This is the solution. Apparently this is the solution. What does it look like? It looks like this. This is called an elliptic curve. Super important actually in life. I'll tell you why, just because I like talking about this stuff. I think you should also like have a great respect and reverence for the following realization. We know everything in math, don't we? About like equations that have x's and y's in them, that have powers of x and y that are 1. Those are called linear equations. We know everything about them when x has a power of 2, right? If you want to do that, those are called quadratic or parabolas, if you want to think about what they look like. Also, or if y has a power of 2 and x doesn't, that we know everything about too. Those are parabolas, also just facing different ways. We also know what happens if we have x's and y's that are squared, both maybe, right? And those together all make up the conic sections, don't they? But the moment we raise the power even by 1 on one of the variables, we get some crazy stuff that happens. And if in that situation where you have one variable raised to the 3rd power and the other variable raised to the 2nd power, you get a series of curves that are extremely important called elliptic curves. And they look something like this. Sometimes they don't have 2 regions, sometimes they have 1. Sometimes they just have like a connected curve that looks like that or something like that. But they're beautiful and they're important, especially in particular surprisingly, in cryptography. It turns out like elliptic curve cryptography is like all the rage now. That's where, in my cryptography class in my master's program, that's where I did like a lot with elliptic curves. But, and it turns out that in abstract algebra and topology, they're like super important, these curves. So, and they figure in very importantly to the proof of Fermat's last theorem, too. So there you go. So just whet your appetite for why a curve like that might be important and not just pretty. Is that obviously separable? Hopefully you're getting a feel for this now. So I didn't even say in the instructions solve the separable differential equation. I just said solve it. Just an IVP. So we get like 1 over cosine squared y. It's actually nice, isn't it? Huh. Yeah, Luke's already there. He's already there. He can't even write faster than he can think. He's so excited that there's a secant squared involved. Yeah. Right? So we're trying to do you some favors along the way, right? Well, we'll just jump right to it. What is it? So much fun to do 2 intervals here. You already had it? No. Throw an integral in there. Luke, you were excited about this. What's the antiderivative of secant squared? Well, see, it's actually not an initial value problem because there wasn't one. So that's good. I mean, I guess we just found the general solution. Are we done? You could, I guess. Yeah, you want to say we're done? Yeah, I guess we can be done. It'd be interesting to solve this for y. Maybe you'd say y is equal to the inverse tangent of x squared plus c. But that's interesting, though, because I think all of us understand that by that we mean, we really mean like the tan inverse function, like the arctangent function that you know, that you learned in pre-calculus and that we've studied and that your calculator uses, has a limited range, doesn't it? So it might actually be better to keep this implicit. So you're welcome to solve that, but if you did, you also have to say like plus pi n or something like that. It'd be weird. Here's the graph of this guy. So if you actually graph on your calculator, y equals tan inverse of x squared plus some number of your choosing. You can choose whatever number you like. I think what you'll find is you only get like one of these guys, right? Maybe this guy right here or something. I don't know. So I obviously chose some value for c to make that picture. Maybe c equals 0? I don't know. Right? Looks like maybe. It's clearly, if c is 0, then 0, comma 0 is on the curve. That's why I'm guessing that maybe I just use c equals 0 there. We having fun yet? All right. By the way, no one expects you to know what this looks like. I just thought I'd share. This time we are actually asking you, please report it as y equals f of x. So is this separable? I mean, that x and y, those are all up together in parentheses. Can we separate them? Yeah, I guess we can. There's only so much I can do to like mask how separable it is. It's separable. It's separable. Y had a negative first, throw a negative there maybe, right? Alright, the calculus is becoming the easy part on this, some of these, right? I know how to take integrals. It's good, I'm glad we spent a whole unit doing integrals. It's good for us. Have some background on this, so that those are easy. So, let's see, I don't know. By the way, there are a couple ways you could do this. You could, at this stage right here, right away, solve for y if you like, right? Or you can solve for c first and then solve for whatever. I mean, you can solve for c at various points in your journey. But I'll solve it. I'll find c right now. What is it, negative 4/3? Check me on that. Is all my algebra good? Okay, great. So then we are still not done then yet. We still need to do some things, other things that looks like other things were asked of us. So I'll write this down, knowing that this is a great way to write the solution, but it does ask us to solve for y. So let's do that diligently here. It's a little messy, but is it okay if I write if I multiply both sides by y, and also simultaneously divide by this mess? Let's see what that gives then. So that'll mean that y is equal to negative 1 divided by 1/3 x cubed minus 4/3. You might even write that as Don't you have an do you have an irresistible? I have an irresistible urge to multiply by 3 over 3. Do you? I don't know. No? No? That look good? There's one more task that was asked of us, though. And that's to state the domain over which the solution is valid. This is an interesting discussion that we need to have now. It's actually not a discussion that AP cares about that much, but it is like a thing that's part of this that's true, and like to be technically correct, you have to say. So I thought we'd like say something about it. Okay. Technically, this solution is well. First of all, there's a place where this isn't valid and it should be obvious. Well, it's not obvious right away, maybe, but do you see a place at the very least where this solution doesn't make sense? Where would that be? Yeah, the cube root of 4 is clearly a problem, but I have more to say than that. Is x equals 1 a number greater than or less than the cube root of 4? It's an interesting question. What is it? Which one's bigger, 1 or the cube root of 4? Yeah, the cube root of 4 is a little bigger, right? So we're gonna. So this point 1, 1 lies to the left of the vertical asymptote. And there is a vertical asymptote on this, right? It's x equals the cube root of 4. It's messy, but okay. So this point 1, 1 is on our curve. You can verify quickly. Plug in 1, and you'll get 1. That's good. So y equals the cube root of 4, or excuse me, x equals the cube root of 4. So this point is to the left of that. So actually the only part of this function that we're going to take as our solution is the portion of the graph that's to the left of the cube root of 4. To the left of that asymptote. So again, this is not part of any discussion that AP would care about, but I just wanted to say right now, like everyone in AP and we too, will accept this as the answer without any restriction usually, but technically this is happening. And this discussion happened earlier in your life too. Let me give you a very simple differential equation that shows this. Like when we showed you a picture of a derivative like this, say, right, here's a picture of the derivative of a function. What is the function that we say this is 1 and negative 1. What function are we working with, maybe? This is a pictorial differential equation, okay? I mean, we could actually write it. This is the signum function. I just didn't feel like writing it, but yeah.
Is that just y equals absolute value of x?
That would be one way to say it, yeah, right? I mean, one picture would be this. What other ways could you solve that, though, besides the absolute value of x? Give me another solution. What else works? Go for some low-hanging fruit. Yeah, certainly. The other thing we could say, I was thinking someone might say right away, you can move it up and down, of course. That's certainly true. But it's worse than that, and so Luke, what are you suggesting? Yeah, what are you suggesting? How do I draw it?
Y equals negative x, and x is less than 0, and x is
Okay, that's still the same solution though, right? Whether you write it that way or not. Actually, I was thinking.
Or you can have like that and that.
Yeah, and that's actually what I was thinking. I think we can all agree that a function like this, and you can put this point wherever you like, that the function like this satisfies the differential equation too, yes? So which is it? Well, if someone gives me an initial condition, then I can nail it down, can't I? They can say like, I need this to be the differential, this derivative to happen, and I need 1, 1 to be on the curve. Well, then I can say, okay, well, I know at least on the right side of this function that the function looks like this, right? It's y equals x for x positive, right? That I know for sure. But how can I, if someone just nails down the right side, how can I know anything about the left side? Do you see what's going on? The same thing is happening with our function we're working with here. This derivative works. The derivative of our function f of x does satisfy this differential equation. So we're beautiful. That's wonderful, beautiful. And the initial condition is satisfied so long as we're on this side of the curve. But how can we nail down the other part of the curve is the question. And the answer is like, technically you can't. This is a plot of the solution curve I just talked about. Okay. So here's that vertical asymptote. By the way, it's kind of a crazy function, huh? But there we go. So y equals, x equals the cube root of 4 is our vertical asymptote there. there's the solution curve we just got. It's written a little different than how we wrote it, but there it is. And that's with that initial condition. And actually, I could actually pull this up because I made this little applet to play around with this. And we could actually slide x1 and y1, the initial condition, around and see what kind of solution curves we get. But just for the sake of time, I won't do that. I did produce one other solution curve with these initial conditions, though. And this is the solution curve you get, right? And the reason I have this is dashed is because, again, that's not really a part we can nail down. Like, that could slide, actually, technically. So I hope you understand the nuance. And that's probably, like, we won't really address that too much more, like, really ever again. I thought you should know the real truth, you know, of the matter. Like, what's going on here. Good. Well, let's do another one. Maybe one more. Sorry, did I see it? I thought maybe I saw a hand. Is everyone good on that? Any other questions, comments? That's a crazy looking one, though. So you need to use some tricky rules of exponents there. Not really, but right, to get that y out of there. This is a little bit. There's a little bit of algebra here to do on the front of the problem to convince yourself that it's separable, isn't there? But so maybe just to make it more obvious, we'll actually like make this happen. So it's sine x times e to the cosine x times e to the y. Right? It's not obviously separable. It wasn't obviously separable before. Now I've made it very clear that we have like a thing with x and a thing with y about it. I can now separate maybe. Yeah, I haven't done it yet, I guess. But I mean, you mean, how did I do that algebra? Yeah. So e to the, or just in general, we have this like rule that we learned back in the day. Yeah. So that's the property I'm using to say that, oh, e to the y plus cosine x, that's just e to the y times e to the cosine x, yes? So, and then I just use some parentheses for decoration, right? That's all, because I want to like really emphasize that this has been separated in a nice way here. All right, so now I think we're ready to do some integration. So we'll move this e to the y over here, we get e to the negative y. Look at that beautiful integral. Looks complicated, but it's actually just a what kind of technique we're going to use it. Huh? Yeah. Beautiful little u substitution, right? Nice one to do. Yeah. E to the negative y. It's actually kind of a u substitution too, maybe, if you, right? Kind of. Maybe just one we want to do in our head, right? Not in both ones we want to do in our head, really. Is that just negative e to the negative y? Right? Integrate that, take the derivative check on anything that we're taking integrals of. And over here, e is a cosine x, maybe with a negative there too, yes? Just check the derivative and check. What's the derivative of negative e to the cosine x? Well, it's the same thing, except times negative sine x. So I think I did it. Lost some constant, still yet to be known. We have an initial condition. There it is, pi over 2. Plug that in, and you should get negative 1. We can apply it now. Now's a great time to apply it. somebody needs to know what the cosine of pi over 2 is. What is it? You thought that was going to be messy, but that's actually, again, us doing you a favor, right? So, yeah, it's 0, so this is just negative 1 over here, and over here we get negative e, right? So, sorry, let me not do too much all at once. So on the left we get negative e, and on the right we get negative 1 plus c. So c must be 1 minus c. Right? Good. It did still say to solve this for y though. So where's our actual equation? There. So it's negative e to the negative y equals negative e to the cosine x plus 1 minus e. Beautiful. Solving for y now. Yeah, we're going to need some logarithms or something maybe along the way. Let me get rid of that negative first, just because I feel like it. So solving for y does require a logarithm, that's true. So that feel to this problem is a little different than what we've had to do along the way before. Yeah.
Did you get the negative when you took the integral of sine x equals cosine x?
Here.
Or am I just not seeing
Is that right here, you mean? So I did do it in my head, but if you'd like to do the u substitution, let u be cosine x, and then du is negative sine x dx.
Oh, right. Okay.
Right? And then, or you could just take, the way I usually think of it is like, I think the answer is e to the cosine x, and then I'm like, wrong? And then I'm like, okay, well, I guess I need a negative, you know? So take the derivative in your head and check. Yeah?
So when you're done with everything, do you not like to shoot those after log through?
You can't.
Can't?
You can't. Do you understand why? It's not like there isn't a property of logs. Think hard about why this is always actually okay, this solution. There's no domain of validity. Is there ever a time when this function will be undefined? Convince yourself that the answer is no, if you can. Huh? Start plugging in all sorts of values here. This will range between negative 1 and 1. See if you can figure out why that's going to be always okay. Have a great day, guys. See you tomorrow for, again, this homework will not be talked about or checked until Monday. Brush up on the thing you need to brush up on tonight, whatever that might be.